It was said in the previous lecture that the wave traveling along a string of springs and pucks that was generated by a periodic forcing along the direction of the length of the string is a longitudinal wave. The definition of a longitudinal wave is that of a wave where the oscillatory motion of the masses of the medium is parallel to the direction of the propagation of the wave. The example in the previous lecture fits the bill. The wave was traveling from left to right, the energy source being to the left of the string. Each puck was vibrating back and forth, going alternatively to the right and to the left of its equilibrium position. Another example of a longitudinal wave is a sound wave. Sound can travel through gas, liquids, and solids. We will concentrate here on sound wave traveling through air. The masses are the air molecules, like molecules of oxygen, nitrogen, and carbon dioxide. The forces between them occurs through collisions that would conserve kinetic energy. We will assume that the air is an ideal gas with no attractive forces that would turn the gas into a liquid. Let us first imagine a room filled with air at a constant temperature, but without sound traveling through it. The equilibrium state of that room is that there is no fluctuation in air density on average. I am neglecting gravity here. It does not mean the air molecules are not moving, but there is no velocity direction that predominates in the room. Any molecule can collide with other molecules coming from any directions. So on average, the molecules are forced through collisions that do not let them wander too much from one location. This is roughly their equilibrium position. Then we turn on a speaker pointing horizontally on the left side of the room. The cone of the membrane of the speaker vibrates from right to left, mimicking a simple wave pattern. For 1/2 of the cycle, the speaker pushes the nearby air molecules to the right, giving them energy that they will share with the molecules ahead of them. We will define the direction with the unit vector x hat. This introduces a new fluctuation to the x component of the velocity in that region. The air is compressed in front of the speaker into a band of higher density compared to the average density at equilibrium. When the speaker retracts, it leaves a region of lower density. Eventually, the cycle starts again and creates another band of high density. The variation of the air density to the right of the speaker gives us a way to describe the wave. The simple model of a wave pattern shown here is over a distance of 2 wavelengths. The air density at equilibrium is indicated by the red line. Do not pay attention to the numerical values for the density. At this stage, I am only concerned with the general shape of the wave. The wave is propagating towards the right, which is in the same direction as the unit vector x hat. The peaks of the density are the sites of compression, while the minima are indicative of rarefaction. But how can changes in density involve net forces that moves the medium as a wave? It is through the fact that the higher the density of the gas, the higher the collision rate between the molecules. Take, for example, a little volume of air here, where the tangent to the curve is the greatest. The molecules in that volume are sandwiched between a region of higher density to their left and lower density to their right. The molecules in the volume are colliding more with the molecules on their left side of the volume than the molecule on the right side, giving a net force towards the right on the molecules of the small volume. If you look at another small volume, which is at the phase of the wave where the air density is maximum, you will notice that the air density on the left of the volume is equal to the air density on the right side of the volume, so the net force on the volume is zero. The same situation occurs at the rarefaction sites. Finally, at the phase of the wave where the density is increasing the most, the air density on the left side is lower than on the right side of the small volume, leading to a net force towards the left of that volume. These forces only have x components. These forces lead to accelerations that have only x components, and will add wave-like variations to the x component of the velocity and the x component of the displacement from equilibrium. Recalling from the lecture on the string of pucks and springs that no net force occurs when the mass is going through the equilibrium position, and that the maximum displacement to the right occurs when the net force is pointing towards the left, and vice versa, we can graph the x component of the displacement of the air molecules versus the distance from the source in this fashion. This waveform has the same wavelength as the variation of the air density and would have the same period as seen from a graph of the x component of the displacement versus time at a specific location. This oscillatory motion of the air molecules is parallel to the direction of the propagation of the wave. This wave is a longitudinal wave. As an aside, notice that the peak of the x component of the displacement of the molecules does not occur when the density is at its peak. So far, our introduction to waves has been reserved to longitudinal waves where the energy source, either a piston or a speaker, is forcing a single period for the perturbation of the medium. The period of the waves created matches the period of the forcing. There are other waves and other physical phenomena that have periods, such as the rotation of the Earth around the Sun. This important piece of information about the time variability of a wave can also be conveyed through a frequency. Let us look at the variation of density that occurs at a fixed location as a function of time for our simple sound wave model. This time, I have given the graph real measurement units. For the air density variations, the measurement unit is in nanograms per milliliter. 1 milliliter is the same thing as 1 centimeter cubed. The mean density of air is roughly 1.2 times 10 to the minus 3 gram per milliliter, so a factor of 1,000,000 greater than these density variations due to the sound. This is why I did not make a graph of air density versus time. You would not have been able to see the variations due to the sound waves on such a graph. On this graph here is the time interval for one cycle, which is called the period. Given the number of cycles, capital N, during a time interval delta t, we can write that the period can be found by dividing the time interval by the number of cycles. For example, looking at the previous graph, we can see that 8 complete cycles occur during 20 milliseconds, giving us a period of 2.5 milliseconds. Another way to report how the wave varies with time is to count the number of cycles per second. This is the definition of frequency. We will use the lowercase letter f for the variable symbol for frequency. If you know the number of cycles during a given time interval, then you can divide the number of cycles by the time interval in seconds to find the number of cycles per second, which is the frequency. A look at the equation for the period leads to the conclusion that the frequency is the reciprocal of the period. Applying this to our example, we get a frequency of 400 cycles per second. This frequency is a bit lower than the frequency of a sound wave of the musical note used to tune an orchestra, which is a frequency of 440 cycles per second. In recognition for the work of Heinrich Hertz on electromagnetic waves, his last name is used officially to be equal to a cycle per second. It is called a Hertz, and the abbreviation is capital HZ. Another important feature of a wave is how fast the wave travels through a medium. We will start with the simple model of a sound wave with a frequency of 400 Hz. Here the wave is described with the variations of density from the mean over 3 wavelengths at the time t equals to 0. The origin of the reference frame is chosen to be at the position of the middle maximum of air density, when t equals 0. The x-unit vector is still pointing in the direction of propagation of the wave. From this graph, it could be seen, even though the numbering is rather small, that this length of wave is 1.5 wavelength, giving this piece of information and leading to the wavelength of 86 centimeters. We will follow the position of this peak of density as the wave moves towards the right. A quarter of the period later, the shape of the curve would look like this. The middle peak has moved to the right of the origin. Another quarter of a period, the graph looks like this, followed by a graph like this after another quarter of a period. We finally get the shape of the curve after a full period. Our middle maximum started at the origin and traveled to that position during one period of 2.5 milliseconds. As you can see, the distance is a wavelength. At this stage, let us recall the equation for the x-component of the velocity of a particle traveling on a straight line along the x-axis. Here we do not have a particle that traveled the distance of a wavelength during one period. We have the feature of a wave that traveled through a medium. This type of speed is called a phase speed and is only defined that way for a wave with a single frequency. We can extend the definition of a speed to the phase speed. The phase speed can then be evaluated by dividing the wavelength by the period. This equation can also be written using the frequency, since the frequency is the reciprocal of the period. Our example leads to a value for the phase speed of 3.4 times 10 to the 2 meters per second. Is the phase speed the speed of propagation of the wave? The problem is that the phase speed is only defined for a wave with a single frequency, which means the wave would need to be infinite both in space and in time. Such a wave does not exist. Only approximation for a finite length that depends on how long the source was supplying the energy. Is the phase speed of a wave the same for all frequencies? It depends on the properties of the medium. For some wave traveling through air, some of the properties that can be relevant are the temperature of the air, the humidity level, the atmospheric pressure, the composition of the air, and the velocity of the wind. To keep it simple, let us only look at situations where the sound wave travels through a typical dry air on a windless day. Evaluating the speed of the wave can be reduced to this equation, which is valid for all frequencies. This means that a sound that is made up of multiple frequencies at the source, such as a chord played on a piano, will reach the listener at the same time. In that situation, the phase speed is the same for all frequencies and is also the speed of the wave. Such a medium is said to be non-dispersive. However, sound traveling through solids is doing so through a dispersive medium. Let us do an example using the previous equation. Here we are dealing with a problem where the frequency of a wave is given as well as the wavelength that is associated with it. So the givens are the frequency and the wavelength. We can find the phase speed of the wave with this equation, and since the wave is traveling through air, the phase speed is also the speed of the wave, which is given by this equation, as long as the phase speed is given in meters per second. We can next isolate for the temperature given in degrees Celsius. Substituting the givens leads to this answer, which is the final answer. So far, we have concentrated our study of sound waves on their periodicity in time and space and on how fast they propagate. But there is another property of these waves that is important, and it is the fact that they transport energy. This will be the subject of the next installment.